Hi, my name is Darren Ramsook, and I'll be presenting on Figure of Merit for Multi-Generation Network for CNSM 2021. The slides are organized as follows. First, we have an introduction where we will go over the overview, then the problem, and also the solution proposition. We'll also look at the component performance metrics, and finally the computation of our proposed solution. We'll do a lower level aggregation and a high level aggregation. Also, we'll have an illustrative example and finally conclusion. Okay, so we know that the upward trends in mobile wireless communication subscribers coupled with the digital content demand has led to cross-generational technologies. For example, mixture between 2G, 3G, 4G, and 5G. This rapid technology advancements means that current wireless communications operators will have a collection of disparate cellular technologies to accommodate their user base. So their user base will be a collection of 2G, 3G, 4G, and 5G customers. And this disparate cellular technologies can be attributed to certain users being unwilling to upgrade to a newer technology, or the provider having to recoup the initial investment for that specific technology. This problem is more severe for developing countries, as many developing countries do not have the infrastructure in place to do technology migration, and depends on amalgamated cross-gen systems to service remote areas. Network management calls for KPIs to be used for measures of quality of service, and scores are also necessary for network maintenance and growth. However, they're very difficult to manage across multi-generational networks. For solution proposition, we propose a mathematical framework for generating a single figure of merit for a multi-generational network. We incorporate quality of service and quality of experience metrics that allow for a high-level monitoring and can be further decomposed by radio access technology, 2G, 3G, 4G, and 5G, and varying services within those technologies, such as voice calls, web, and SMS. The scores used are derived from network probes that are at the very edge of the telecom network. The figure of merit is essentially the probability that a customer uses any service on any technology and receives acceptable customer service. So the score always lies between 0 and 1. And this score and all other calculated scores are provided through an interactive hierarchical diagram, so errors that propagate to the final figure of merit can be easily detected and evaluated. So within the context of this paper and presentation, the network we used was assumed to have the following properties. The network consists of only digital-based radio access technologies, such as 2G, 3G, 4G, and 5G. A single base station can support any combination of technologies, so it can support 2G, 3G, 3G and 4G, or any combination of those. Web services for 2G networks are delivered via General Packet Radio Service and Enhanced Data GSM Evolution. The 4G technologies use circuit switch fallback for voice calls and SMS messages through the existing 3G network. And the 5G network uses Evolved Packet System fallback so that voice calls and SMS are delivered through the 4G circuit switch fallback protocol. This figure shows the hierarchical nature of the figure of merit. The single figure of merit can be decomposed into 2G, 3G, 4G, or 5G branches. Within each generational technology, there are scores attributed for voice, web, and SMS. And behind each aggregated voice, web, or SMS scores, there's a collection of quality of service or quality of experience metrics that create those scores. In the following slides, we'll show an example of how scores are propagated through the network's edge, which would be represented by these quality of service and quality of experience scores, all the way up to this single figure of merit. Okay, so the figure of merit is based on the probability that an action taken by a customer is successful and is completed in a satisfactory manner. We assume independence between events and compute the probability of satisfactory events for each technology. So we let P sub S Rn represent the probability of a satisfactory completion of service S on a radio technology R over a time interval N. So for example, one service might be web, R might be 2G, and N might be 24 hours. So now we show an example of calculating score for 2G voice calls. This score is represented by the area enclosed by the red rectangle in this figure. So the score for voice, which is PV Rn, where R would be 2G, is calculated by looking at the proportions of a collection of other quality of service and quality of experience metrics. So for example, we look at the proportion of drops that were called within the past 24 hours if N was 24. Similarly, we look at how many calls were successfully set up in the past N hours and how many calls were set up with an acceptable delay and how many calls were received a certain specific quality. We take those proportions and multiply it by each other to get the final score for voice 2G. So this process is repeated for other services and other technologies. So for example, for web, this same process would be repeated and so on and so forth. So the scores derived for voice, web, and SMS are then aggregated a level up. So the service FOM score is a weighted combination of the service metrics. So each technology is weighted based on the proportion of the revenue that is derived from that service. So the services are voice, web, and SMS within each 2G, 3G, 4G, or 5G technology. And these scores are aggregated together within each technology to provide a radio access technology score for radio access technology R. And mu S is the proportion of revenue derived from service S. So again, aggregating over access technology now, we use the proportion of subscribers in each radio access technology in calculating a weighted value for that technology. So here the final score, Pn, is the weighted sum of alpha R, where alpha R is the proportion of users in technology R multiplied by the service level score calculated in the previous slide. Okay, so the table on the right shows real-world data collected over a period of 7 days for a multi-generational network. So each period represents a time frame of 24 hours. So period 2 has a loss in 2G and 3G voice calls, while period 5 has a loss in 5G web services. The final row on the table on the right shows the final figure of merit score for that given day. If we look at these scores, we can see that the drop associated with period 5 is more severe than the drop with period 2, as the weighting factors used for revenue and subscriber proportions are different. So we could see that in period 5, the loss in 5G web services had more impact than in period 2, where the loss in 2G and 3G voice calls occurred. So in general, the following equation holds. The change of the final figure of merit score with respect to the score for service over a given subscriber base is mu S alpha R. Mu S is the revenue for service S and alpha R is the number of subscribers in that technology R. So this indicates that the rate of change for the FOM for a given score for a given technology and a given service is directly dependent on the amount of revenue and subscribers in that service. So the final figure of merit platform is separated into three distinct sections: the data input and also the processing from the network probes, data warehousing, and front end. In our development, we use a period of 24 hours to refresh our calculations and update the front end scores. And also the main interaction point of the front end was a dynamic tree map interface, and this allowed the users to see through a color code the lower performing sections of the network and the higher performing sections. So in conclusion, we propose a mathematical framework for a single figure of merit on a multi-generational telecommunications network. So we use various quality of service and quality of experience scores in different technologies. The usefulness of this approach was demonstrated using data sampled from a real telecommunications network that experienced poor service. In future, other quality of service and other quality of experience scores can be integrated, such as video streaming scores. The platform also serves as a data collection point, so over time, certain insights and predictive models can be developed to detect network performance